All right. Good morning, everybody. Welcome to our lecture on game AI. This is lecture 13. And our topic we are currently studying is still very much the question of clustering waypoint maps. We'll continue that study for a couple of lectures to come. But recently, we've seen that if we represent a game map in terms of a graph so as to capture its geometry, we would encode the geometry of the game map by means of vertices of a graph, where we label the graphs using 2 or 3D location vectors, and we would also encode the topology of the game map, that is transitions, potential or possible transitions between waypoints could be encoded using edges or links of such a graph. And then we studied an idea as to how to cluster such graphs, and that was called spectral clustering. And it is somewhat outrageous that this idea of spectral clustering actually works at first sight. However, if we look under the hood, we can actually make sense of that algorithm, and this is what we are about to do. So 2 lectures ago we met the idea of spectral clustering, and then in the last lecture we spent some time on basic mathematics, and today we will make use of that mathematics in order to understand the physics behind spectral clustering. And once we are through with that, you are one of the few people on the planet who understand what you are doing when you are doing spectral clustering. It is somewhat baffling to me that it appears just from reading the scientific literature that many people use this technique but have no idea whatsoever as to what they are doing when they use that technique. So let's get started. What we did in the last lecture was that we familiarized ourselves with the notion of the Laplace operator. And that is interesting insofar as when we do spectral clustering, we have to compute something that is called the graph Laplacian matrix. And one would wonder where this name comes from, or why one would want to compute the graph Laplacian. Now we have met something else that is named after Laplace, the Laplace operator. If we are given a function f of a vector x, that is, if we are talking about a scalar field, this is some function that assigns every point in space a number, we call these things scalar fields, then the Laplace operator of that scalar field is given as the sum over all the second order partial derivatives of that scalar field. And that was for the case of continuous functions f of x. When we are dealing with graphs, we are dealing with discrete structures. And so therefore we also looked into how to define the Laplace operator for the case of discrete functions. I am using square brackets to indicate discrete functions in contrast to continuous ones. And once again, it is just given as the sum over the second order partial derivatives of that discrete scalar field. So a discrete scalar field is a function that does not assign a value to every point in space, but just to certain points on certain grids, say. The Laplacian of a scalar field is the divergence of the gradient of that scalar field. Here is a scalar field. Here is the gradient, which is to say a vector field. And on the right-hand side, we actually have a visualization of the Laplacian of f. Even though these two figures look rather similar at first sight. They are not. Right? There is a difference between this one and that one. Please convince yourself that there is a difference. Do you see anything that is different? Like this, like, I don't know, this is different here, or it's not the same. So, that is the Laplacian. And something we need to be aware of, not many people are aware of that, at least in computer science, which is a shame because, you know, computer science is all about operations on data types. This Laplace operator is a function of functions. That is what it turns that into an operator. This is to say, it takes a function and produces a function. This is wrong here, that should be R to the no m there. It takes a function and produces another function. And we either have that for the continuous case or the discrete case. So this thing here is an operator. Operates on functions to produce new functions. And in fact, it is a linear operator. That is, it has all the properties we would ask from something to be linear. Some of the outrageous things we discussed in the last lecture, again, they are basically outrageous to computer scientists, which is a shame, is that labeled graphs can be understood as discrete functions, that discrete functions are vectors, and that linear operators are matrices. And note that I've actually skipped the discrete here. So linear operators as we know them, say differentiation, can always be understood as a matrix, even though the vector space for which this operator is defined might be of infinite dimensions. It may be a Hilbert space. Nevertheless, linear operators are matrices. And we saw that there is a one-to-one correspondence between the Laplace operator on a discrete function and the application of the graph Laplacian to a vertex label vector. If we represent the discrete function in terms of a graph and therefore look at the vector of all the vertex labels, then computing the Laplace operator of this discrete function is exactly the same as if we were to apply the graph Laplacian matrix to this vertex label vector. So there is a one-to-one correspondence between these two situations. They are identical. The Laplace operator is a staple in physics. We'll basically encounter it a lot. Plays a very important role in many areas of physics. And the particular area of physics we are interested in today has to do with waves. And here is the wave equation. Let u be a function with two arguments, x and t, and that is to say, let u be a function of space and time. In the world we live in, we can understand x as indicating a point in space, some three-dimensional point, and t would indicate, well, a point in time. Cannot actually, you know, I can do it like this. So that's points in time. Wave equations are defined like that. We look at the second derivative with respect to time of this function u, and this is supposed to be equal to a constant that is called c square. C is called the speed of the wave, so c square times the Laplace operator of that function u of space and time. And I thought, before we continue, it is probably a good idea to look at a couple of waves. So in order to understand what a wave, well, really is a bit of a euphemism, but let's look at a couple of waves. What we see here is, what is it? It's a line. It's a good idea, yeah.
It's a string.
Pardon?
String.
Maybe it's a graph.
It's the most boring wave.
Yeah, it's a very, very boring wave, and it's a very boring graph. Look at this. There are vertices, right, and edges in between. We can also think of this, for instance, as, say, water molecules, and I don't know, say, van der Waals forces in between these water molecules, something that sort of tries to keep them together. Or think of it as a spring mass system. So these dots indicate masses, and the edges in between the dots would indicate springs, right? Or think of it as a very large spring, I don't know, a slinky, and for some reason I have emphasized certain parts of that slinky in terms of dots. Now, what I will do is I will excite this vertex. Let me talk about graphs, but think of this as a spring mass system or water, whatever. I will excite one of these things here, and that will cause a distortion. And what I'm doing here is I'm simulating what this equation we just saw tells us. So let's go for it. Have you seen it? I, somewhat excited it and then moved it back down, and that caused a distortion. And this distortion is now traveling along the structure, like so. And once it hits this end, something interesting will happen, because I actually fixed this vertex. This one here cannot be distorted in this particular simulation. All right, so let's see what happens. Aha! This wave got reflected. And note that that had the effect that what used to be a mountain on the way towards this end of the system now has become a valley. All right, let's see how this continues. Apparently now I have fixed it on this other side as well, and it's a very boring wave. It's actually a horrendously boring wave. Okay, this is a more interesting one. Same thing, all I have changed in this simulation is sort of the magnitude of the force in between those masses, and so therefore we have some more interesting behavior sort of at the tail of the wave. But once again I have fixed it, right? So it got reflected over here, and now the mountains from the way towards this end of the structure become valleys. Yeah, and that continues like that. This is a wave in one dimension. What's happening here is, like, the playlist is playing without me to ask, so I have to live with it. What we see in this simulation that just started is more or less the same situation. This time, however, it's not just one distortion or excitement, but a continuous distortion and excitement on this side of the structure. So if you look at this, this will continue to go up and down. Think of my hand, pulling that slinky up and down. That has the effect that it's not just one wave or like one peak that is traveling along the structure, but now this is something we'd actually call a wave, right? It has several peaks and valleys. And again, I have fixed the structure at this end of the spectrum. And now look at this. There are waves traveling from the left to the right, and because of the reflection at this end, once it has reached that end of the structure, there will be a wave traveling from the left, from the right to the left. All right? And these two kind of waves, the ones that move in that direction, because here there is a continuous excitation which causes waves to move in that direction. And now once they reflect over here, there will be waves traveling in the other direction. Those two kind of waves will now begin to interfere. And that looks like this. Yeah. So sometimes, if there's sort of a continuous excitation and waves, real waves, not just one peak, but a lot of them travel in one direction, and then there is some sort of reflection going on so that other waves travel in the other direction. They will interfere. Sometimes a peak meets a valley, and if that happens, they will cancel out. Sometimes a peak meets a peak, and then resonance happens, and the thing becomes really heavily excited, and that causes dynamics like that. And I guess in the simulation that has already begun to play this time, what I did is I actually did not fix, where are we? Did not fix this point here. I guess in the, I don't know for sure, but I would assume that in this simulation, wave 4, this thing is allowed to move freely. So let's see what happens. Yeah, moves freely, but once again, interference happens. Sometimes things cancel out, sometimes they enforce each other. That is the behavior of a wave on a one-dimensional lattice. And note that I'm continuing to excite the system at this end of the spectrum here. All right, so excitation, excitation. And now, something that is of extreme interest for what we are going to study today. If this structure is excited at a certain frequency, say on this end of the lattice, if I, take this thing and move it up and down in a certain frequency, we will observe this behavior. This is called a standing wave. What is happening here is that indeed the forward movement and the backward movement are in sync, say, such that there are certain points where they will always cancel out. So it appears as if this point here never actually is distorted, and this is because the frequency of the wave is such that the forward and the backward traveling waves at certain points always, not just sometimes, but always cancel out. This is a wave, but it appears to stand. Right? It does not move forward. It does not look to us as if it was moving forward, but it sort of stands. If this excitation is slightly faster, but once again done at a certain specific frequency, we'll observe this. Right? It's another standing wave. This time there are actually 2 points of the wave that do not move. There's one more. Actually 2 more. Here's another standing wave. Sort of 1, 2, 3 points of the wave that hardly move. Note that the frequency is higher. and here's yet another one. Again with higher frequency, and frequency means the amount of, or like how fast sort of is that movement, right? But if I excite this system with this frequency, it will create another standing wave, which is to say certain points of that system hardly move. Okay. And now we need to understand this. This differential equation describes the dynamics we just saw. And if we look at differential equations like that, the question could be, well, this is basically an expression as to, well, given some function u of space and time, then this should hold. But how does this function u of space and time have to look like? Our goal right now is to solve this wave equation, and we'll make an informed guess. There's a beautiful German word in mathematics that actually cares. We make an Ansatz. And our informed guess is to say that this function u of space and time can be expressed as a function v of space only and a function w of time only. All right, this is why should that be? Mathematical convenience. If we make this assumption, it will turn out we'll come up with a solution to our problem. So therefore, this is what we will assume. Let us assume this unknown function u of x and t could be expressed like that, as a function v of x times a function w of t. And if we then do this and look at the wave equation, we'll find, let me go back for a second, on the left hand side we have a derivative with respect to time, second order derivative, and here we have second order derivatives with respect to space, right, Laplace operator. So if we do that, then on the left hand side we have function v of x times w of t, and we have to derive that 2 times with respect to time. V of x does not depend on time in our ansatz, right? So the left hand side becomes v of x times d2 dt square w of t, because in this form of the function only w depends on t. This is a constant with respect to time. On the right hand side, it's the other way around. We have c squared times w of t. W of t is not a function of space, it is a constant with respect to computing the Laplace operator. So we have c squared w of t times Laplace v of x. Right? And then we can say divide both sides by v of x, that goes down here, and we divide both sides by w of t, that goes down here. We therefore find w dot dot of t over w of t equals c squared times Laplace of v over v. And note the funny thing I've done here. On this slide, I'm using the so-called Leibniz notation for differentials and the Newton notation for differentials. Like, this is funny because they were in a bit of a quarrel about who invented it first. Here you see them both. This w dot dot is just a shorthand for d squared dt of w. Right? This is how Newton wrote it. And there you have it. With our ansatz, that u of x and t can be written as v of x times w of t. The wave equation becomes that. Let that burn into your brains for a second. So on the left-hand side, there is something that involves this w, and on the right-hand side, there is something that involves x, or v, I should say. W is a function of time, and v is a function of space. But that is to say that the left-hand side of the wave equation we obtain under our assumption now is a function solely of time. There's no x on the left-hand side. And the right-hand side is a function solely of space. There's no t on the right-hand side of that equation. In order for a function of time to equal a function of space for every time, every point in time, every point in space. Pardon? Einstein. In order for something of time to equal something of space, and not only for a particular point in time, t naught, and a particular point in space, say x naught, but for all t and all x, this can only hold if this is a constant and this is a constant. There is no other way, right? Because they are two functions defined with respect to two different things, space and time, and they're supposed to be equal. This is left-hand side is a function of time, rather complicated function of time. The right-hand side is a function of space, rather complicated function of space. But it's a function of time and a function of space, and the wave equation tells us they are supposed to be equal, and that can only be the case in this situation if they are constant. All right? And therefore, I will call it gamma. And we can therefore write the second derivative with respect to time, w dot dot of t, as gamma times w. So this is now really easy. What I did here is I just multiplied this w of t over here. So we have w dot dot is gamma times w of t. And at the same time, we get that the Laplace operator of v of x is gamma over c squared times v of x. And I'm too lazy to write gamma over c squared, so I shall call it lambda. Right? But that is then to say that Laplace v equals lambda v. Ah. You already saw what's going on. What is happening here? This is, it looks as if it has to do with eigenvalues and eigenvectors, right? Right, because we have some operator, important, this is an operator, applied to something is supposed to be the same as a scalar times that something. Right, and you already said it, well, that looks as if we are in this realm of eigenvalues, and we know it as eigenvectors, but now we are talking about functions here. Right? And so it is indeed the case that, and now we have a generalization of what we all know, it is indeed the case that this function v of x is an eigenfunction of the Laplace operator. What are eigenfunctions? Have you ever seen an eigenfunction before? Let me tell you, all of you have. But nobody may have told you that you have seen an eigenfunction. First, let us recall sort of what I hope you all know, at least the ones who study with me should be able to tell me about this at 2 at night if I wake you up, because this features prominently in basically all of my lectures, the spectral theorem. If we have a matrix M, positive semi-definite symmetric matrix M, there is a theorem that says we can factor it in terms of a matrix U, a matrix lambda, and then that matrix U transposed. Those matrices U here, in the case of symmetric positive semi-definite matrices M, are, we know that these matrices of the eigenvectors are orthogonal matrices. They are in the group of orthogonal matrices. Therefore, the inverse equals the transpose. So if we multiply both sides of this equation with the matrix U from the right, then this U transpose times this matrix U would cancel. We would get M times U equals U times lambda. And this is now sort of, with respect to a matrix, applied to, say, all columns of a matrix U. We can look at that column-wise. We would find that matrix M times a column U of this matrix U would be the same as a eigenvalue lambda times that eigenvector lambda, because I didn't say this matrix lambda is a diagonal matrix. Everything is 0 except for the elements along the diagonal. So this is called the spectral decomposition of a matrix M. And for each vector U and each scalar lambda for which this holds, we say that U is an eigenvector of that matrix and a lambda is an eigenvalue of that matrix. And now remember that we learned in the last lecture that operators are matrices, right? And certain matrices have eigenvectors and eigenvalues. And I said, like, even though these operators may live in extremely high dimensional spaces, infinite dimensional spaces, we can still think of them as matrices. We should not. So for the mathematicians among us, please don't think of them as matrices. Everybody else is allowed to think of them as matrices. But you should think of matrices as operators. That's the correct way of thinking, but it's a bit... So we know that certain matrices may have eigenvectors and eigenvalues. And last time I said functions are vectors. That is definitely the case. Functions do form vector spaces. And I said that linear operators are matrices. I should have, put it the other way around. So for mathematicians out there watching this, matrices are operators. That's the better way of casting it. But given our discussion, we may think that if vectors are functions and matrices are operators, then why shouldn't operators have eigenfunctions? Here is an example. This is an operator, ddx, applied to a function f of x, and it is supposed to produce lambda times f of x. So this looks like an operator, or a matrix times a vector is a scalar times a vector. Right? Of course, we are now doing this with functions which generalize matrices and vectors. Operators generalize matrices, functions generalize vectors. But have you seen this before? You should have. What would I have to say f of x equals? Some exponential something, yeah. Let's have a look at this. Aha. I told you that each and every one has already seen eigenfunctions. There you go. The exponential e lambda x is an eigenfunction of this operator. Who has seen this before? Have you been told that the exponential is an eigenfunction of the derivative operator? Why not? Why not? something has gone horribly wrong in your undergrad education. Look at this. This is something we know from matrices and vectors, but it holds apparently in more general settings as well. So therefore, we can actually live with that statement that I said the function v of x we are currently actually interested in is an eigenfunction of the Laplace operator. But wait a minute, this is just sort of the first derivative. Could we have the same for second derivatives, such as they occur in the Laplace operator? Does this thing have an eigenfunction? Can we solve this for f? Like, we can write down the equation, but can we actually solve it for f? Yes, there we go. Actually, there are two solutions this time. These e to the square root of lambda times x and e to the minus square root lambda times x are eigenfunctions of the second derivative. And just looking at these two rather simple examples, you now understand why this function here is so utterly special in mathematics. This is rather special, and you understand the special role of the exponential when you find that it is actually an eigenfunction of derivatives. All right? But long story short, operators like these things, this is something that takes a function and produces another function. Operators may have eigenfunctions. And if we look at these waves, they are functions of space and time, because something happens over time, and whatever happens depends on where it happens. Well, we've seen like this wave traveling, there is some dynamics going on, and at different spaces along that line there was something else happening. So waves are functions of space and time, and if we split the function u of x and t into a component v of x times a component v of w of t, then that v of x would represent the spatial dynamics of an oscillatory distortion that spreads through a medium. So an oscillatory distortion that spreads through a medium is called a wave. All right? V of x represents the spatial dynamics of the wave, and solutions to where was it? Solutions to these equations, like once again, this is sort of what we found from looking at the wave equation. We found that v of x is supposed to be an eigenfunction of the Laplace operator. Solutions, those particular functions v of x for this actually hold, are called standing waves. We've seen them, right? So if we can solve this equation 3, that is, if we can find a function v of x that would be an eigenfunction of the Laplace operator, then that would indicate an eigenmode. This is another fancy term of this oscillatory spreading process, but these eigenmodes are also called standing waves. And if the carrier medium is a discrete structure, say a graph, such as we saw in the pictures or videos we saw, where we have these beads on a string, or these spring mass system things, or these vertices with edges in between. If we are talking not about continuous functions but discrete functions, then what we worked out last time would translate to the fact that Laplace operator v of x something continuous equals lambda times v of x something continuous. What we worked out last time translates to this. Laplace matrix times the label vector equals some scalar times the label vector. You had a question?
Yeah, I had a question.
In order to get standing waves,
Yep.
we need to have special boundary conditions for the equations. What is the meaning of these conditions in discrete case?
In the what case?
In discrete case, so in just a graph.
It's actually the fact that, you know, last time I sort of hand waved away the fact that for a finite graph, not all the vertices have a degree of 4 when we talked about those grid graphs last time, right? But some of them at the boundary may have a degree of 3 or a degree of 2. Those are, you know, those corners of those grids. That's basically like these conditions you worry about are encoded in here in the special structure of the Laplacian matrix. So it's actually really nothing we need to be afraid of here. This actually, it is simpler in the discrete case than it's in the continuous
So
case.
the idea that we don't have more than 4 degrees of freedom.
Yeah.
Okay.
Yeah. So once again, last time we talked about grid graphs, basically, you know, lattice structures.
Yeah.
And if they are finite, then there will be a point in some corner where there are only 2 edges, right? Like the majority of points will have 4 neighbors. Points along the boundary will have 3 neighbors, and then there are certain points that only have 2 neighbors, right? But this is encoded in that matrix, and we really do not have to worry about that. It's actually, like, in a certain sense, it is easier to look at these equations, and this is why you all learn about this and not about this. Right? And I have to say, I also know, I only know that because I studied physics, right? So that gives me an edge. But yeah, the thing is, for discrete structures, which we sort of excite such that a oscillatory distortion spreads through the structure, the continuous Laplace equation here can be written as indeed a matrix eigenvector eigenvalue equation. Right, and that is of course the equation we solved when we did spectral clustering. And that is to say that in a certain sense, and really careful here, those are metaphors, but I want you to understand why you solve this here when we do spectral clustering. So in a certain sense, solutions to this equation indicate basic spatial dynamics, and as always, from the area of differential equations, we know that if we have a couple of solutions to a differential equation, we can create yet another solution by just linearly combining some of the solutions we have. So every dynamics of such waves can be expressed as some combination of all the standing waves. And different eigenvectors of this Laplacian matrix indicate different standing waves. And we've seen the rather slow one, and then there was like even faster and so on. And depending on the frequency, there were different points that never moved. Now, for those of you who've been with me in the last semester, I'm looking at you, when we did spectral clustering and I said, let's look at the Fiedler vector, which is a name for the eigenvector of the graph Laplacian that belongs to the second smallest eigenvalue. And I said, the entries of the Fiedler vector indicate whether or not a vertex in a graph belongs to one cluster or the other. They are either positive or negative. And now, knowing that the Fiedler vector is actually the eigenmode where there are 2 hills and valleys, you know, moving interchangeably, we all of a sudden understand why the Fiedler vector works as a way of cutting a graph into 2 parts. In all the videos we saw that if there is a distortion spreading throughout the structure, then nearby points move similarly. right? Like it's very unlikely that if there's a hill over here that there's a valley immediately next to it. The valley is sort of farther away. Similar points show similar oscillatory behavior. And the Fiedler vector, that is the vector belonging to the second smallest eigenvalue, has, you know, just one thing going up, one thing going down, one thing going up, one thing going down. And so therefore that is actually really a vector that would allow us to divide the vertices of any graph into two groups, namely the one that's going up whereas the other is going down, or vice versa. So there you have it. Different eigenvectors indicate different standing waves, and similar vertices have similar dynamics. And so therefore the solutions to this eigenvector-eigenvalue equation we consider when we do spectral clustering should indeed allow for clustering. Let me see what I have here. The important thing is really not so much, I don't know, the length of edges or whatever, but if we look at the graph Laplacian matrix, it is basically the graph degree matrix minus the adjacency matrix. There are other variants, but at its heart, the simplest way of talking about this is the graph degree matrix minus the adjacency matrix. These two things, degree and adjacency matrix, are solely topological aspects of a graph, have nothing to do with how far the vertices are apart or where they actually are. They really just encode relations. And spectral clustering therefore relies on relations in terms, encoded in terms of edges. That does not only apply to grid graphs. Right? We only talked about grid graphs in the last lecture because it is fairly easy to make the connection between discrete functions and grid graphs, but it does not have to be a grid graph. The funny thing is, and this is always baffling to me, but once again I studied computer science and physics, so if you read about why spectral clustering works in the computer science literature, it's so convoluted an argument, it is almost maddening. It's like I consider it laughable. We now understand that the eigenvectors of the graph Laplacian correspond to standing waves on a graph. And that's basically it. And it says that if you look at waves on a discrete structure, then similar vertices of that structure should have similar behavior. And we can look at the behavior in terms of the entries of the eigenvectors of those graphs and actually understand them as a feature representation of the vertices. I'll say something about this in a minute. Let me see. Yeah, I'll get back to that. Let's have a look at more videos first. I said this does not necessarily only apply to grid graphs, but of course the examples we have seen so far when it came to encoding dungeons, those were grid graphs, so I'll stick to the grid graphs. However, it is not a line graph anymore, right? It's now a somewhat more interesting structure. And when I created those videos, I had to face the following problem. Either I would have created a three-dimensional plot where something moves up and down, but that was somewhat of a mess. Lots of meshes and like hard to see, blah blah blah. Or I would create it in a representation like that, where instead of having something moving up and down, I would use color to indicate whether it's down or up. And we can see this here. Can you see it? That this here is I don't know, bluish, and this is purplish. Different colors. Okay. Let's go for it. It's very hard to see, I admit that, but there is. Wait a minute. Let's start. It is somewhat hard to see, but there is a dynamic going on here. And this is actually, in this case, the dynamic encoded in the first eigenvector. Right? This is just, let's start again. There's a standing wave here. Something goes up, goes down, goes up, goes down. And it is the wave that would correspond to the first eigenvector, and we see that it subdivides this thing into two parts. And the division is actually here at this point. And that makes sense. It makes a lot of sense. And we can now understand that physically. There's something going on here, down here say, and then there's this bottleneck, so it's somewhat of a problem to get this dynamic from down here to up here, but once it is here, then that part of the system shows a certain behavior, and there you go. I have also, yeah, I don't know, this one is probably even harder to see, I don't know, it is the second eigenvector. Let's see if we can see some dynamics. Note that in the upper structure there is now a different kind of dynamics going on. So actually, can you see that this one is brighter than these two? So this second eigenvector now allows us to distinguish the upper part of that dungeon. The third eigenvector, I should say, right? Because the first eigenvector of these graph Laplacians is always the vector of all ones. That one is uninteresting to us. That is the wave that is constant. It's also a wave. It's also a solution to that equation, right? But that one is of very little interest, so we are interested in the first one, the Fiedler vector, and then in the, oops, how do I do it? Like, you know, second one, and so on and so forth. Let me see. This one is now the fourth eigenvector, so again, totally different. I don't even see anything anymore, and maybe you do, but I don't. I guess I have one more, yes. Fourth one. You see that at least the frequency is going up, something we found as well in the case of line graphs. Oh yeah, this is the eigenmode 8, flickering. But we can use the information encoded in these eigenmodes to subdivide the graph into parts. 13th eigenmode. I don't even know what that means anymore. This is, you know, even though we can picture it, it's still hard to understand what that actually says. So, and when I said that we can use these eigenvectors as representations of the nodes, what I meant is that we have the graph Laplacian and we compute its eigenvectors. We throw away the first one, the constant one, that is really of no interest whatsoever. We keep the second one, say the Fiedler vector, if we're interested in subdividing the graph into just two subgraphs, and if we're interested in more groups in the graph, we also look at the third eigenvector and the fourth eigenvector. So what we end up with is a matrix, column matrix, of a couple of eigenvectors we keep. Couple of eigenvectors, columns in a certain matrix. And for every vertex in the graph, there will be a row in that matrix. So that is to say, the rows of that matrix formed by the columns which correspond to eigenvectors of the Laplacian. Those rows are representations of the vertices of the graph. Right? And if we therefore perform clustering, as I said you should, on the rows of that matrix, this is a way for us to identify vertices of similar behavior. Right? And depending on how many groups we want to identify, we need higher and higher eigenmodes of the Laplacian. Here are some general properties of the graph Laplacian. It is symmetric the way we defined it. Other people have different definitions, but for symmetric graphs, this graph Laplacian will be symmetric, and it's also positive semi-definite. And we already discussed it last time that the smallest eigenvalue of L is always 0, and that the corresponding eigenvector can be understood as the vector of all ones, or make it some other constant. Doesn't really matter. I'll make it all ones. Maybe you want to verify that at home. Write down the definition of the graph Laplacian and think about what it means to multiply that particular matrix with a vector where each component is a 1. And then you immediately see that the corresponding eigenvalue has to be 0. Do that at home. Because of these properties, we know that the eigenvalues are non-negative, and we can order them. And sometimes it may happen that there are a couple of eigenvalues of a value of 0. So that is to say, the second smallest eigenvalue does not necessarily have to be the second number in this ordered set of numbers, but it is always meant to be that number that is the first number greater than 0. Sometimes there are several zeros here, and whenever we find that, we can rest assured. We know for sure that the graph we are dealing with is not a connected graph. Right? We talked about a couple of concepts from graph theory, and I said a connected graph is a graph where every vertex can be reached from any other vertex. And if that is not the case, in the sense there is, I don't know, one disconnected group of vertices and another disconnected group of vertices, this graph would not be connected. And if you give me any graph, and I could compute the graph Laplacian and its eigenvalues, just from looking at the resulting eigenvalues, I could tell you whether or not the graph is connected. If it is not connected, there will be at least 2 zeros. And if it consists of 3 not connected components, then there will be 3 zeros. And if there are 4 not connected components, there are 4 zeros. That is to say, the multiplicity of the eigenvalue of a value of 0 indicates the number of independent or not connected components in that graph. Oh boy, that's actually all for today. I thought those videos would take more time. You now know what it is you are doing when you are doing spectral clustering. There are also other interpretations, other physical interpretations, but you can really think of what you are doing when you are doing spectral clustering as investigating the graph in terms of an oscillatory system or the network you want to cluster. When you do spectral clustering, you understand it as a system through which a certain distortion is spreading. And whether or not you understand it as a diffusion process or a wave does not matter that much, but if you understand it as the carrier medium for some distortion, you know that these kind of distortions in physics always involve the Laplace operator, because distortions are functions of space and time. And with respect to discrete structures, the Laplace operator becomes the Laplace matrix. And today we saw that when we solve wave equations, that's basically about eigenfunctions of Laplace operators. And once again, when it comes to discrete structures, then that becomes eigenvectors of Laplace matrices. Similar points in a network should have similar dynamics. We can look at the entries in those eigenvectors in order to identify vertices of similar dynamics. And in passing, we got to know the notion of standing waves and eigenmodes on discrete structures and how they are connected to graph Laplacians. That is indeed really all for today. Do you have any questions? Once again, to me, one of the really, in a sense, most horrible things as somebody working in artificial intelligence, machine learning, and so on and so forth, is to see that many people just parrot certain recipes without ever understanding what it is they do. However, as the next generation of scientists and engineers, hopefully expanding the knowledge of mankind, you need to know what it is you're doing so that you can actually contribute to it, right? And now you know why spectral clustering works. And that has nothing to do with game AI. I give you that, but this is a master's course. And we have to, look beyond simple recipes of, given that we do this, we always have to ask, why do we do this? And how does it work? And how could I possibly improve on it? That is the question you should ask yourself. Great, so then, see you on Thursday.